Okay, let's get started. Welcome back. I have two short announcements, just logistics. One is, are there any questions about last week's exercise, what we did on Thursday? You still have time. If you didn't finish, you still have time to work on these problems on your own. And then on Thursday, during class time, Iskander will upload the solutions. Upload means he will push them to the solutions branch, and then you can check them out on Git, merge them into your main branch, or leave them on solutions and keep working with what you did. That's number one. Number two is recordings. As I said, we're trying to do recordings. Last Thursday it failed, and I think it was sometimes we screw up. That happens too. But last Thursday I think it was some equipment malfunction because we turned the microphone on, and even there we already saw that the display is not reacting. So we're hoping that this maybe the display was broken, but apparently the microphone was broken. So we're trying to fix that or have that fixed until Thursday, but my apologies, right? There's no recording with sound. And in general, right, if you miss a class, if you're sick, if you have a conflict, send Iskander an email and we can give you access to the recordings. So we will do that, but only upon request. Any other questions that you may have before I dive right in? No, I have been talking about sort of fundamentals. It's still a summary, so we will move very quickly through these topics. We talked about vectors, how we represent them using coordinate systems. What you see here is basically an equation that tells you how to go from the numerical representation, these coordinates v1, 2, 3, and a coordinate system C giving me the description of a physical vector, just scaled versions of the coordinate axis being summed up, and this gives me my physical vector. And then we talked about the opposite direction, where we basically take measurements, and where we take measurements by using a physical dot product, which is basically a projection. So here, what I'm doing, I'm projecting the vector of interest, v, onto my three coordinate axes. So I measure the length of this vector along these three coordinate axes, and that exactly gives me my numerical representation, my coordinates. And that's why the dot product is defined the way it is, right? This doesn't happen by coincidence, but the dot product is defined such that we can do this. Here we've been talking sort of about operations, and what's I think most important to me is that you always keep in mind there's sort of a physical world where you don't need numbers. And then on the right-hand side, we see the same operation done on coordinates, yielding, of course, the same result. In a computer, we are always doing this, but in the background, this is what we want to achieve. And we talked about the cross product. There is a second product that you all know, which, we talked about the dot product. Now I want to talk about the second product, which is the cross product with a very similar definition, right? Length of one vector times length of the other vector, or magnitude times, now here we have the sine of the angle between these two vectors. And then we also have this additional normal vector, right? A vector that is normal to v and w. And so the result that we get here gets basically scaled with n. So we get now a vector as a result, not a scalar value. Who has seen this, right? That the length of this vector is defined as the area of the parallelogram spanned by v and w. You've seen this, right? Yeah, please don't think of it, think of the cross product that way in this class. I'm not saying this is wrong, but it doesn't really help you. The way you should think about the cross product in this class is, again, as a projection, right? With the dot product, we basically took v and projected it onto w because we used the cosine of the angle. Now, using the sine of the angle, we are projecting v onto a direction that is orthogonal to w. So it's very similar, but projecting not sort of onto a vector, but to a space that is orthogonal to a vector. And that's and we will use cross products when we talk about rotations, and that's basically what's happening. If I have a vector of interest v that goes from my point of where I am, my location, somewhere to some point of interest, and at that point of interest I'm interested in some vector, the dot product will project. And sorry, in this I should define this as my view vector looking from me to a point of interest. The dot product projects onto this vector, so basically giving me information how things move away and towards me. The cross product projects onto something that's orthogonal to that vector, basically telling me how things move around me, right? I'm basically ignoring the information about going away or towards me. I'm just looking how is this thing moving left and right. And that basically gives you this close connection to rotations that we see with the cross product. We have the numerical definition of the cross product over here. And we can show very easily that I can write a cross product also as a matrix multiplication. I hope all of you have seen this at some point. If not, it's very easy to verify that this matrix multiplication using the matrix defined down here is giving me exactly the same result. And I will very freely switch between these two notations, going from a cross product in this notation to sort of a matrix vector product doing the same thing. This is often more convenient when we implement things, particularly in MATLAB, where sort of the basic computational unit is a matrix, but it's also sometimes easier to show certain things. And this is the matrix with this tilde operator, a skew-symmetric matrix, zeros on the diagonal. The off-diagonal elements are sort of opposite sign. Quick question, is this matrix invertible? All right, let's do this differently. Who thinks this matrix is invertible? Who thinks this matrix is not invertible? All right, do you want to give me a reasoning why?
The determinant is 0.
Okay, how do you know that the determinant is 0? I would be careful with that, because you can easily construct matrices that are. Yeah. So that's mathematically, that's not enough to say the diagonal is 0, so it has to be, the determinant has to be 0. Do you have another idea?
I thought it's because, maybe that's also wrong because of the trace, but I think it's just the thing you said.
Yeah, that would be the definition of the trace. What's your thought?
There is a vector v such that when we multiply it to the matrix, we get 0.
Okay, so there's a null space, so that would tell me that the determinant is 0. So I think if we go ahead and compute the determinant, we will see that it's 0, but that requires some more consideration. There's a much easier argument to say why this matrix is not invertible, why it's singular.
I mean, if we take the cross product of the vector with itself, it's always 0, so this vector lies in the null space. It's basically the same argument.
That would be a nice argument to say if I multiply the vector v with this, I will get 0. But more general, right? What we see over here, what I just discussed, is that cross products are projections. A large number of vectors v, right? I could draw my vector v to this point here, and it would project to sort of exactly the same value here, giving me the same cross product. It's a projection, so multiple vectors will give me the same result. And that means that this matrix here also represents a projections, and projections cannot be inverted. The same way that I cannot invert a cross product, right? That's something important to keep in mind. That's something we will need in this class. If I give you a cross product, a vector v and a vector w, and the cross product of these should give me another vector u, and then, sorry, I give you v, I don't give you w. I ask you what's w. That is not a well-posed question, because there's infinitely many w's who can do Those are sort of the main operations. Always keep in mind that's physics. This is what we actually want to achieve. This is how we achieve it. And then, of course, the coordinates that we get here are the coordinates that we would get from this vector that results from the operation on the left-hand side. Then I want to move on into coordinate transformations, which are basically dealing with the question that if I have a vector v, right, this is the vector v here, which is something physical, exists before I introduce any coordinate system. What did I do right now? So I have this vector, and then someone, colleague of yours, went through the trouble and identified the coordinates of this vector v in some coordinate system c. So if this is given, you now want to know what is that vector in a different coordinate system, let's say in the d coordinate system, and so you want to know the coordinates vd. Right? So that's basically the question that we have to ask ourselves. And again, the best way to think about this is that physics are there without any coordinate system. So in doing this transformation, I go through the physical vector. Right? I use my original coordinates and the original coordinate system C to compute my physical vector or get a representation of this physical vector V. And then I apply sort of this measurement equation where I take the dot product of this physical vector V with the coordinate axis of the D system. Right? So these coordinate axes, I think I didn't note them here, but these would be the coordinate axis of the C coordinate system, and I use them to get the vector V, a physical vector, and then I go ahead and take measurements along the three axes of the D coordinate system, and then this will give me here my vector coordinates of the same vector in the D coordinate system. And then I can just plug this equation into this equation, pull out the numerical vector VC, the elements that you see here, and evaluate sort of the dot product between V and, between D1, C1, D1, C2, D1, C3, and I end up with this matrix here, which is our transformation matrix. So it's a very compact way of writing. I have these numbers. I want these numbers. How do I get them? I get them by multiplying with this 3x3 matrix. This is what we will call a transformation matrix. In the literature, you will also see this as the direction cosine matrix. Who has an idea why this is called the direction cosine matrix? Abbreviated sometimes with DCM. Why is this the direction cosine matrix? Think about the definition of the dot products that we have here. Right? Magnitude of first vector times magnitude of the second vector times the cosine of the angle between these two vectors. And since these are coordinate axes, they are of unit length. So the product that I get here is simply the cosine between these two coordinate axes. So this is a matrix full of cosine terms, and the angles correspond to the angles between the individual coordinate axes in all possible combinations. If I want to do the opposite, right, I have my numbers given in the D coordinate system. I want to know what are the numbers that represent this vector V in the C coordinate system. I could go through the exact same process. The only thing that would change is that every time where I had a C up here, I now have a D, and vice versa. So these two expressions are exactly the same, just that I flipped the roles of C and D, which is now basically giving me the back transformation. And since dot products commutate, so this here, D1 times C1 under the dot product, is of course the same as C1 times D1 under the dot product. We see that this matrix here is the transpose of that matrix, which is noted down here. And since this is the forward transformation, backward transformation, one is also the inverse of the other. And we can immediately see that the product between ACD and ACD transposed is equal to 1. That's a well-known property of these orthonormal matrices. They're called orthonormal because the columns are orthogonal to each other, and all columns and all rows have unit length. The way you should think about transformation matrices, apart from these rather abstract definitions, is, oh sorry, and I'm changing my notation because I'm trying to make this align better with other lectures. This is the identity matrix. I will write this as E. This is a German Einheitsmatrix, a German abbreviation, but that relates better to the other classes that you've heard so far. So ACD times ACD transposed, or ACD times ADC, is the identity matrix. The way you should think about this is if I look at a particular vector, the vector C1, that's the first coordinate axis, the x-axis of my coordinate system C. And now I go ahead and represent that in the C coordinate system. It gets a very simple representation, 1, 0, 0, right? I'm describing the C1 coordinate axis in the C coordinate system. That gives me this definition, 1, 0, 0. And now I want to know what is the representation of this vector C1 in the D coordinate system. And I just apply this transformation matrix ADC multiplied with the vector given in C coordinates. And if I do a matrix product with such a vector, what I obtain is the first column of this matrix. So the first column of this matrix ADC is the vector C1, the first coordinate axis of the C system expressed in D coordinate axis. And of course, I can do the same for the second and third coordinate axis. So what a transformation matrix basically is, the way you should think about it, is the coordinate axis of the original coordinate system expressed in coordinates of the target coordinate system. And that's not really surprising because these are linear operations. And if I can transform the coordinate axis, I can transform any scaled sum of the coordinate axis. And that's basically any possible vector that we can think of. Good. Any questions so far? Now things get a little bit philosophical for a moment because I now want to talk about vector derivatives. And if we talk about vector derivatives, we first basically have to agree what does that mean, right? Derivatives is about things changing. And what do we mean, right, physically? Not thinking about coordinate systems yet, but what do we mean if a vector is changing? So if I give you a physical point A, right, and I really mean this is not a drawing of something, that's the point I'm talking about. And this is a physical point B, right, that just happens to be on this blackboard, which is convenient. And then I can go ahead and draw a vector R, A, D. And my question to you is now, is this vector stationary, right? Does it change? So who thinks this vector is stationary? Show of hand. Who thinks this vector is moving or non-stationary? Nobody. What happens if I do this? Does that change your opinion of this vector being stationary? Who now thinks this vector is stationary? Okay, who thinks now this vector is moving? Okay, so no.
We have to watch the vector in
Okay, this is where we're getting with this discussion. So first of all, me moving the blackboard has no influence because vectors have no origin, and as long as I just move this sort of parallel, which I hope these guides are good, right? The vector doesn't change. Right? It's still the same vector, whether it's down here or up here, even though the points change. Right? The points change, they change their location, quite obviously, but the vector is the same. I would still argue that this vector is not stationary. Right? So when we talk about non-stationary vectors, maybe that's sort of the first take-home message, is we're not talking about translating them. Right? We have to talk about something else, namely rotating them. Right? Vectors changing their direction or changing their magnitude, not changing where we draw them. I would still argue that this vector is changing, it's rotating. Why is it rotating? Earth rotating, right? So this vector is sitting there and rotating around the sort of north-south axis of the Earth once every 24 hours, right? It's even rotating around the sun at an even lower rate. So there is clearly a rotation. And we see now that this idea of whether a vector changes or not is not something that we cannot answer absolutely. Because even if I say, okay, now relative to our solar system, I draw this vector. Is it rotating? Yes, no, right? I compensate for the rotation of the Earth. Well, Earth is moving around the sun. We can cancel that. But then, is the sun really stationary? Is our solar system really stationary, or is that rotating? And then if it's rotating, against what? Right? So there is no notion of something being absolutely addressed. And if you were taking a physics class, this would be the point where I would start talking about frames of reference, where in physics, not even in relativistic mechanics, people would sort of emphasize this idea of a frame of reference, that every experiment, every observation you do is subjective and depends on where you are and what you do. Right? Are you stationary? Are you moving? Are you accelerated? Are you non-accelerated? And so on and so forth. Right? And this is a frame of reference, which is a very abstract concept, but I can think, to simplify things, of this room here as a frame of reference. I can think of the solar system as a frame of reference. And what we see is that the question of whether this vector is stationary would give you different answers. And this is where then physicists sort of drop this notion of absolute things, and whenever they do something, they would report in what frame of reference they did it. And then there's equations to go from one frame of reference to another, but it's never sort of absolute. Now, this is not what I want to do for this class, because I want to keep things a little bit more simple, because by the end of the day, we're doing robotics. And if I think about robotics, if I think about accelerations that happen in this classroom, they are dominated by gravity with about 10 meters per second square. If I look at the acceleration that is caused by the Earth rotating around itself, that's 0.03 meter per second square, so magnitude's lower. And then if I think about the Earth rotating around the sun, we get 0.006 meter per second square. So this is sort of me being an engineer. Whenever I give you a value of g, I say it's 9.81, which already tells you that I may not care about anything to a higher precision. And that allows me now to basically boldly claim that this room is stationary. And this is an assumption that is arguably wrong. If this was a class about satellite dynamics or orbital path planning, right, we would not make that assumption, but in a robotics class we can make that assumptions. And that's my definition, that this classroom, or any classroom, fortunately, on campus is going to be an inertial frame of reference that I consider to be stationary. And whenever I talk about a vector derivative, I mean a physical derivative against this stationary inertial frame of reference. Normally, I would always have to tell, if I talk about derivatives, I would have to tell you in which frame of reference, but we're not going to do this. So whenever you see a vector derivative, it is in our inertial frame of reference. And then if I think about derivatives of vectors, well, what can I do with vectors? I can add them up, I can scale them. And so I look at my vector at some time t plus delta t, subtract where it was at time t, divide this whole thing or scale it with 1 over delta t, take the limit of delta t against 0, and I get my vector derivative. And this is basically here my physical definition of a vector derivative, right? The derivative of a physical vector is a physical vector again. And we define that in an inertial frame of reference, which we just say is something that is not moving or not rotating. That's the important thing here. If it's translating, that doesn't matter. It's also not accelerating, or at least accelerating, as I said, right, in some way that we can neglect. And this is how I define my derivative. So whenever you see the notation of a vector, right, and this vector, we have not talked about coordinate systems, very important, right? This is just sort of a Euclidean physical vector, and here is its derivative. And I don't need coordinate systems to do this, but I need a sort of a frame of reference just to make this drawing here, right? The important thing if I make this drawing is that I draw my vector at time t, and I draw it at time t plus delta t, and that I don't rotate my screen or rotate the frame of reference. And if I assume the frame of reference is stationary, as this board is, then this would be the vector at time t plus delta t. I get the difference, I scale the difference, and I get another vector. So this is what I mean with a physical derivative, which for this class, and other people do this differently, right? But for this class is going to be a physical derivative in an inertial frame of reference. If I think about an example here, I mean, this is basically what we always had in mind. We think about positions, right? Positions are not vectors, so we have to think about relative positions. So there's a vector from point O to point P. The point O is a stationary point, again, relative to this inertial frame of reference, or in this stationary in this inertial frame of reference. So stationary in this room, the point P is moving. So the vector ROP is a function of time, and I get a velocity, which is the physical derivative of the vector ROP, which I write as the velocity from point O to, or the relative velocity of point O and P. Now, if this point O is stationary, there's basically a simplification that we can make that we see over here. If I pick a different origin, right? If I describe the motion of my point P not relative to O, but to relative to O prime down here, of course my vector ROP is going to be different, right? ROP points from here to here. RO prime to P is pointing this way. So different positions, of course, because we use different points as a position reference. And then I can just use the vector sum to get RO prime P as RO prime O plus ROP. If I now take the derivative of this, right, to get the relative velocity of O prime to P, right? This expression here, I can get this as the sum of the derivative of this plus the derivative of this. And then this first expression here, by definition, is equal to 0. That's almost my definition of an inertial frame of reference, that I have these points that are all stationary and that the vector between these points doesn't change, so its time derivative is 0, right? So this vector derivative here is 0 if both points O and O prime are stationary. Which means that we immediately see that the relative velocity of RO prime P is equal to the relative velocity of ROP. And we will just define this now as the absolute velocity of point P. So I dropped the O because apparently it didn't matter what I picked as my reference point, as long as it's stationary and as long as all reference points are stationary reference points, it doesn't matter. And so I'm saying this point P has an absolute velocity. And if you really want to say relative to what? Well, relative to any stationary point in this coordinate system, right? So it just doesn't matter. Good. So this is the most important thing. This is what I mean when I talk about physical derivatives. Change of vectors in this frame of reference that we sit in, which is our classroom. Does not need coordinate systems, right? Frame of reference and coordinate system are completely different. Not the same thing. Now, of course, we want to do math, right? And if we want to represent moving vectors or changing vectors, we have to live with the fact that the numbers that represent these vectors will also change. So in addition to sort of these physical derivatives, we now have to reason about coordinate derivatives or numerical derivatives. And that basically leads me to an important distinction. Because if I talk about the derivatives of coordinates or coordinate derivatives, I can think about two potential definitions or two different derivatives. The first one is that I care about the numbers. So I care about the coordinates of vector u in the C coordinate system. These are just 3 numbers. And these numbers may change. And I would get a derivative. How do these numbers change over time? That's one way of looking at coordinate derivatives. The other way, when I talk about coordinate derivatives, is to say, well, I care primarily about the physical derivative. So du dt, as we've seen above, is a vector, right? That's the physical derivative of the vector u. How does it change over time? That change over time is again represented as a physical vector, right? If these are relative positions, if u is a relative position, this is going to be a velocity, right? So something physical. And any physical vector can be expressed in C coordinates. So you see there's a bit of a difference in order. Do I first create the numbers and then look at the derivatives of the number, or do I first create the derivative of the physical vector and then look at the number of that derivative? Oh! Pull out your glasses. So these would be the derivative of the coordinates. And over here we have the coordinates of the derivative. And on the left-hand side, we would have a numerical derivative because we're just looking at how do numbers change. Here we have the coordinates of this physical derivative within our inertial frame of reference. And I will introduce a bit of notation that is simply saying, if I just write this, right, my dot notation, you see dot, I mean what we have on the left-hand side. So the derivative of the coordinates against time. If I want the thing on the right-hand side, I would use parenthesis. U dot is the physical derivative, and that is being expressed in c coordinates. So this would be what we just had, du dt, and then the result is being expressed in c coordinates. So that's a very important distinction, right? And whenever I use this abbreviating dot notation, please keep in mind what I'm trying to express, right? Sometimes if I want to be even more explicit, I would, oh, pardon me, I screwed this up. I would use this notation where I say, let's look at the numbers, and just for emphasis, I put in parentheses and then put my dot on top, which is the same as writing this, right? So this is just emphasizing this order a little bit more, and if you compare this style or this expression with this expression, I think it's easy to now see the difference in order. And this is on your next page. Hopefully you have the C here. Now, why bother? Right? Why do I care or emphasize these two different definitions? Why this distinction? Right? Isn't that the same? Why should the order matter? So what's the issue that we're trying to preempt here? Has to do with the fact that my coordinate system, C, is not necessarily stationary. And then again, if I mean it's non-stationary, means it moves relative to our inertial frame of reference. So stationary coordinate system, an inertial frame or inertial coordinate system sits still here. Could translate, but I mean these are vectors, doesn't matter. A moving coordinate system moves relative to our inertial frame of reference. And if we think about physics being first, I have a vector and I have a coordinate system which comes second, which always comes second, right? Someone put this coordinate system here, put it there, doesn't matter. I get numbers, the coordinates of this vector. Now the coordinate system rotates, the numbers change, right? So my numerical derivative, the expression on the left, is non-zero. What about the vector derivative? The physical derivative? 0, right? In this room, it's shaking, right? I'm excited to teach and then, but sort of big picture, stationary, right? So no physical derivative, but the coordinate system moves. So I apparently get changing coordinates, which are non-physical, right? The numbers, goes back to the example that I showed in the last lecture, where we had this idea of changing units, right? Things stay the same, but they seem to be different because the units change. Here, my coordinates change and the numbers change. So this is why these two are not necessarily the same. Because my coordinate system C can move. And if I look at how we define vectors sort of as the scaled sum of my coordinates, sorry, there's no vector on here, with the coordinate axes. And then look at the derivative of this, I would have to apply the product rule, and then I basically, for the change of the physical vector, I would get the change of the numbers. Come on. Times the coordinate system, but with the product rule, I would also have to look at the change of the coordinate system. So I get C dot here, and this happens for the other coordinates again, right? And if I think about this is my physical vector, and the things that stand in front of my coordinate vectors, my coordinate axis would be the coordinates, right? I immediately see that this, the changes of U1C, is not a coordinate of this because we have these additional terms. With one exception, and this is now this idea of a stationary coordinate system. Only in a stationary coordinate system, my coordinate axes don't move, so they have a physical derivative of 0. This is 0, comma, only if my coordinate system C is stationary. So only in a inertial coordinate system or inertial frame, so any coordinate system that is not moving, and we're going to call these coordinate systems I, these expressions here are 0, and then what is left here is that I basically have my coordinate axis scaled with the numerical derivatives, and I see that these numerical derivatives are indeed the coordinates of the physical derivative. So only in such an inertial frame the coordinates of the physical derivative are the same as the derivatives of the coordinates. Right, so if my coordinate system doesn't move, I don't have to worry about this issue. But if the coordinate system moves, I have to account for this motion of the coordinate system. And this brings us now to sort of the next topics of moving coordinate systems. Yeah, sorry, you have a question. Did I screw up somewhere? Yes. Sorry, no, go ahead. So these are, oh, this is wrong. Yes. So that's where I screwed up. Of course, right? These are scalars, right? These are the coordinates, and then this is a vector. This is a vector. No, that's the only one you complain about, right? Or you saw another one too?
No,
Just that one. Okay. Yeah, sorry. No, this should be a scalar. You've seen this in other classes, that it is always beneficial to use moving coordinate system, right? At this point, it seems easy. If you just have this information, you would be tempted to say, let's do everything in inertial coordinates. Why even bother? But moving coordinates make representations much more compact and actually easier down the road. So we will be using a lot of moving coordinate systems. And I will start by introducing a naming convention here, where I is a stationary or inertial frame or stationary coordinate system. That means the same thing. And what it means is that if I put it in this room, come back a day later, it's still going to be in the same orientation relative to this room, even though relative to the sun, it has rotated around itself. Yeah, but that's my definition. B is a so-called body-fixed coordinate system that is attached to one of these rigid bodies that we look at in this class. That could be the segment of a robot. This could be the chassis of a car. This could be the shank of a human body, right? These could be rigid bodies, and I would attach a coordinate system to such a body, and it moves with this body. And then sometimes, very rarely, we use an arbitrary coordinate system. And then I use the symbol C, letter C. Good. And if I talk about moving coordinate system, the one thing that I'm curious about is how to do derivatives. And the answer to this question is very simple. I don't, right? I transform everything into an inertial frame. What does that mean? Well, if I have a vector u, and that is given in C coordinates, and C is a moving coordinate system, I just apply a transformation, AIC, to get the vector in I coordinates. And since C is moving and I is stationary, this transformation AIC is a function of time. That's how I know that C is a moving coordinate system. And that would give me the representation of my vector u in this inertial coordinate system. I then can go ahead and take the time derivative of what I have here, right? And here I have numbers, right? UIC, the coordinates of u in I, the I coordinate system. And so I basically take here a numerical derivative. And this numerical derivative follows from the product rule by taking the derivative of my transformation matrix. I have this new computer, and it's very sensitive to me doing dots. Still have to get used to this. Do a dot. All right, I'm gonna do circles. These are dots. Due to technical limitations, my circles are now dots. But product rule, right, I also have to take the derivative of the original number. So That's my, my product rule. And since we did this in an inertial frame of reference, I know that whatever I get here is the same as the coordinates of my original, the coordinates of the physical derivative of the original vector. And this sign here, this equality, that only holds in inertial coordinates, right? Never do this in another coordinate system. Never do this in a moving coordinate system. But in an inertial coordinate system, we can do it. And then I can go backwards, because what I want to know is what are the coordinates of the physical derivative of this vector u in the c coordinate system, right, where I started. That's what I want to know. So I have to now do the back transformation. So I just apply ACI, still a function of t, to this original vector u, which we computed in I coordinates. And if I expand that expression, I get ACI times AIC dot times the vector u expressed in c coordinates plus ACI times AIC times the numerical derivative of the coordinates of u in C. This thing here is the identity, right? ACI times AIC. That is forward-backward transformation. That just gives me the identity. And then here we have ACI times AIC dot. What type of object is that? Right, we have two 3x3 matrices that we multiply with each other. Right, don't be fooled by the fact that one has a dot on top. If I take the time derivative, numerical time derivative of a 3x3 matrix, I will still have a 3x3 matrix. So a product of two 3x3 matrices is going to be, again, a 3x3 matrix. And I will call this, give this a name, and I will call it omega tilde IC expressed in C coordinates. And we just use that definition for now. And now I take this result and rearrange it slightly. And I will get from back here, right, this guy, I pull to the left. These are the changing numbers of u in the C coordinate system. And they are given by the fact that the vector u may have a physical derivative. It's changing. And that change is expressed in C coordinates, minus this additional term, omega tilde IC in C coordinate, times the original vector u, with this 3x3 matrix omega tilde being defined as ACI times AIC dot. And who can tell me what the meaning of the second term here is? Right? This is clear, right? The physical vector changes. So if the physical vector changes, the numbers should change. But what is this second term? What's happening back here? What's being described here? That's the rotation of the coordinate system. So what this equation says is, hey, you have numbers that represent the vector u in the c coordinate system, which is moving. Those numbers will change, right? This is the derivative that we write here. This is how your numbers change. These numbers will change a because the vector may change, right? The position changes over time. I'm describing the position of a point. I don't know, my nose, right? And now my nose is moving, physically moving, visibly moving in this frame of reference. There is a change to the physical vector. And of course, if the physical vector changes, the numbers representing the physical vector should change. But also B, the coordinate system can rotate, right? And if the coordinate system rotates, but my vector remains stationary, the numbers should change, reflecting just the rotation of the coordinate system. And this is the second part here. And then there's sort of this weird special case that we will see a lot, where these two, right, I could have just this, where my coordinate system is stationary, my vector moves. I could have just this, where my vector is stationary and my coordinate system moves, right? I could have one or the other. I could have both at the same time, right? And then I could have this very weird exception where these two are exactly the same. What would be the example of that?
Maybe that the coordinate system moves, like the movement of the coordinate system and of the vector cancel themselves?
Yeah, and that seems weird, right? Weird coincidence. Why should this term be exactly that term, right? That seems like an odd coincidence, but we will see this actually a lot, because if I take a vector and the coordinate system and they're both attached rigidly to the same rigid body, they will always move with each other. And in this coordinate system, my vector here is going to be 0, I don't know, 30 centimeters, 0, right? And then I move around. I have physical motion, right? I have a physical derivative. This vector has a physical derivative. But what are the numbers? Still 0, 30 centimeters, 0, because that coordinate system moves together with the vector. So in such a body-fixed coordinate systems, the numbers will never change, but I have a physical derivative, right? So that's, again, something that we will see, that this term here on the left is going to be zeros. The numbers are constant, yet we still have motion. The motion of the physical vector and the motion of the coordinate system are just coupled to each other, and so I always get the same numbers even though things are changing. I want to take a quick break here and see if you guys have any questions. It seems simple now, and my experience is, I mean, this is not the first time I'm teaching this class. In 3 weeks, you will start confusing the different types of derivatives. So that's why I didn't only treat that as a repetition of, I assume all of you have seen this before, but I went through it in more detail. And if you feel lost, think about this room. Think about this room as your ultimate reference, because this room is stationary. And if something changes relative to this room, ignore the numbers, ignore your coordinate system. If something changes relative to this room, it has a physical derivative. That's, to me, the most important thing. Now, small detail, right? I wrote this here as omega tilde, kind of indicating that this is a skew-symmetric matrix. And of course, that's true. That's easy to show. If I look at the following product, ACI times AIC, right? Forward and backward transformation multiplied with each other. That's just going to give me an identity. And now I will go ahead and take the derivative of that expression, which means I have to apply the product rule. In this case, I get, I don't know, I got so beautiful dots. And now there, here we go. And then also repeat this with the dot on the other factor. This here is exactly the definition of omega tilde that we had before. Omega IC in C coordinates. This one here I need to manipulate a little bit, because I can now go ahead and instead of writing this as ACI, I write this as AIC transpose with a derivative on top, times, and I do the same here, ACI ACI transpose, which if I pull the transpose out, I get ACI times AIC dot transpose, which we immediately see now is omega IC tilde C, with, of course, a transpose. So what I get here is omega IC tilde plus omega IC tilde transpose, which is equal, and now I have to look to the very left of this equation where I started, the time derivative of the identity matrix. So that is equal to 0. So what I see here is that omega IC tilde is equal to minus omega IC tilde transpose. So this is a skew symmetric matrix. So it's equal to minus its transpose. And that means what we're looking at here is a cross product, just as we discussed it at the very beginning of this class. And that gives me a different way of writing this equation as the time derivative of the coordinates of u and c is the coordinates of the physical derivative of u minus the cross product between a vector omega IC, which we also assume is being represented in the c-coordinate system, times the original vector u. In the English literature, this equation is referred to as the transport theorem. And then in TM3, you've seen this as Eulersche Differentiationssatz. So those are basically the same thing. We will call it transport theorem throughout this class. And then on the next page of your template, you have all of this pre-written. And all I want to add here is, again, this interpretation of the equation, which is the most important thing. On the left-hand side, we have the change of numbers. The numbers that represent u in the C coordinate system, they change. That's what this derivative means. And they change, well, potentially, because the vector changes. Or the vector could be stationary, but the numbers would still change because the coordinate system rotates, so we have a change of the cosis, and then these two things could happen at once, both contributing differently to the change in numbers, and those two things could also happen to cancel each other, leading to numbers that stay constant, which doesn't mean that the physical vector is stationary. In terms of notation, we identify this vector, right? The vector that is basically underlying this cross product here, which is underlying the skew-symmetric matrix, as the angular velocity of the coordinate system C against the inertial coordinate system I, which in itself is a vector. And this vector is given in C coordinates. So we have basically three coordinate systems here. We have a reference coordinate system, a moving coordinate system, and then we have in blue the coordinate system in which we provide the vector. And those three could be completely different. This is how we define it, right? But no one will hold me back to pre-multiply this with the matrix A, B, C, right? And express this vector in B coordinates, right? Then I would have the vector omega IC expressed in B coordinates, would still be fine, right? Since it's a vector, this is my standard vector transformation as discussed previously. If I think about the skew-symmetric matrix, it's a little bit different because I have to do a matrix transformation, and matrix transformations always take a transformation matrix AIC before the matrix that I want to transform and one afterwards, right? And that seems odd at first, but if you think about it, here I think of this as a vector, and the vector is just being transformed, right? Going from one coordinate system into the other. Vector is a linear combination of basis vectors. I transform the basis vectors. I transform the vector, right? Here, I think of this as an operator, right? An operator that takes a vector in by something that I multiply to it on the right and gives me a vector back, which is then the cross product between these two vectors, right? I can think of this as an operator that takes the cross product with omega. And here I now need two coordinate transformation for such an operator because I have sort of the vector that I put in that comes in some coordinate system, and now I need to transform basically that vector into the vector of my operator, apply the operator, then I get a result in the coordinate system of the operator, and I need to transform that result back into my original coordinate system. And this is basically what we see here, right? Assume over here, right, this operator is in the I-coordinate system, so it takes a vector in the I-coordinate system, it spits out a vector in the I-coordinate system. And here I basically see the same thing. So taking a vector in the I-coordinate system means multiplying it from the right. Multiply it here. This vector through ACI get transformed into the C coordinate system. So if I have some vector in I coordinates, multiply with this, I now have a vector in C coordinate systems. I apply the operator given in C coordinate system, which gives me the result in C coordinates. And then I use AIC to basically transform the result from C coordinates into I coordinates. And those 3 steps are identical to doing the entire operation in I coordinates. So that's also something that you should keep in mind. And then if I apply this, for example, to our definition, just as a side note, because we're going to need this in one of the exercises, omega IC tilde is defined as AIC dot times ACI. Right? But that follows from this definition up here after applying these transformations. Okay, those are now derivatives. Yeah, very important because we talk dynamics, so we will not only talk about positions, but we'll talk about velocities, accelerations, and so derivatives are at the very core of this class. Do you have any questions about derivatives? Hard to believe. I trust you. And if questions pop up until Thursday, I will give you another opportunity to ask them. I want to move on now and want to basically now use these tools that we develop to describe the motion of rigid bodies. So I want to talk about rigid body motion. And you already see it here on your slide. If we think about rigid bodies, right, we first have to come up with the definition. What does it mean if a body is rigid? Well, if I think of a body as a collection of individual points, and those points never change their relative distance to each other, right? If I pick any 2 points, track them over time, their distance remains constant, then I would say such an object is rigid. And that shows me that these orthonormal transformations, these coordinate transformations, could be a very good tool to representing rigid body motions because they exactly do this, right? What I'm saying here is that the distance between any 2 points, and this distance is now expressed as a vector u, right? Magnitude of a vector u, that remains constant. So the square root of the dot product of this vector with itself should remain constant, right? The body can rotate, of course, so the vector changes, but its magnitude remains constant. That's our definition of a rigid body. And then I can write that either in C coordinates or in B coordinates. And if you basically apply the coordinate transformation, expand, realize that this product here gives you the identity again, you see that it doesn't matter which coordinate system we use. So we see that basically this distance metric is invariant to coordinate transformations. And thinking about it the other way around, it gives us a tool to use transformations to describe rigid body motions. So these transformation matrices, right, our ACD or ABC, have now 3 meanings, right? The original meaning, how we introduced them, where we said we use them to convert coordinates from one coordinate system into another. We then almost implicitly use them to define a coordinate system, right? Numerically, I mean, I can define a coordinate system physically by just, buying one and physically putting it in the room. But this is, of course, not how we're going to do things. We will put one coordinate system in the room, our inertial, in our inertial frame of reference, we will put one stationary coordinate system in a well-defined location, nicely align it with some features of the room, and then describe any other coordinate system relative to this original coordinate system. And this relative orientation of these two coordinate systems we describe as well with a transformation matrix. Right? Exactly the same object, slightly different meaning. Right? In one case, I use it to transform vectors. In the other case, I actually use it to define what do I mean, where's the coordinate system C? Well, we agreed on a coordinate system I, and here's a transformation matrix AIC, and from that you now know where the coordinate system C is, right? And I can do this with other coordinate systems, C1, C2, B coordinate system, and so on. And now we add a third use of this transformation matrix by using it to describe rigid body motions. Right? And all of a sudden, we are leaving this very clear separation that I tried to keep up until now of the physical world and the numbers. We always said the numbers are arbitrary because someone put a coordinate system in there, and they could have put it in a slightly different orientation, and the numbers would all be different, and the physics wouldn't change. Right? Now we couple them, because we now say, in order to describe the motion of a rigid body, we attach a body-fixed coordinate system. Right? Of course, you have a choice how to attach it to this body. Everyone in this class would attach a coordinate maybe differently to my lower arm. But where you don't have a choice anymore is that it is sort of rigidly attached to the arm. So once it's created, it's going to move with my arm for all eternity. That's what we mean with body fixed. And this is now where sort of these notions of physics and numerics get a little bit more intertwined. You had a question?
I think there's a mistake in the line where you calculate d squared. I think it should be UB after you expand.
Oh, down here.
Yeah, and also ACB then instead of ABC.
This is funny because I've been using this for about 10 years and it's clearly wrong. Sorry, how to fix this? This has to be a B, so there's no doubt about this.
And ACB instead of ABC.
UACB, ACB. Yeah. Okay, doesn't change the result. Let me make a note. And then we see if people figure it out again next year. Would you believe me when I say I introduced these small things to check whether you're paying attention? No. Could be. Could be. Sorry, here are my notes. So philosophically, I think this is important. Other than that, I think it's simple. I now have my body. I attach a coordinate system to it, and I track its rotation relative to another coordinate system down here. So this would be the B coordinate system up here. Down here we have an inertial coordinate system. And I track this relative orientation by looking at the transformation matrix AIB. I think that is an important notion here, right? That this is a relative rotation, right? Relative to this inertial coordinate frame I, but someone else could have picked an I prime or I2, and then of course my numbers again would be different, but the motion of the rigid body would be the same, right? And there's no sort of absolute orientation, but always a relative orientation. And that only gives me rotations. I also need to track positions. So I need to fix a point on the body, again, body fixed point, and I need a fixed stationary reference point in my inertial frame of reference, and I track again the relative translation between these two quantities, right? So orientation and translation are always relative. And in the future, I will draw this point B here at the origin of the coordinate system. I think this is how you know this, drawing the point I here at the origin of this coordinate system. Here, I just separate it to make sure you understand that these are two different things. That's all I need. And using basically this coordinate system and this point, I can now go ahead and compute the position of any point on a rigid body. You've seen this, so I can do this fairly quickly. Is basically, if I think about positions, I need to basically say I need the position of point Q given relative to the stationary point I. That's the position of the point B plus this vector RBQ from B to Q. And then you see that we express everything in these body fixed coordinates B here. And that's a very, very central idea to what we're doing here. And it's very practical. Why? Right? Why don't I write this equation here in I coordinates? Why do I write it in B coordinates?
Because the numbers are constant because it's a rigid body.
Yeah, because coordinate system and vector live on the same rigid body. We basically have to express these numbers once, measure them once. Yeah, sometimes in my robots, it really physically means measure, where we've been sitting in the lab and trying to figure out what is that relative distance, and then express it in some coordinate system. And there's a physical measurement that takes time, but we have to do it once. And from then on, know that these numbers will never change because the vector that we're expressing in the coordinate system are moving together. And we see this down here when we now start talking about derivatives, where I say, what's the velocity of this point Q? Well, that's the velocity of point B plus the relative velocity between B and Q. And here you see the parenthesis. So this is the physical derivative expressed in B coordinates. And I now go ahead and use the transport theorem to expand it. And I get the numerical derivative, which we know it's 0, right? That's exactly the special case. Vector and coordinate system are on the same rigid body. This derivative is 0. And we're basically left with the motion of the coordinate system that fully describes to me how this vector RBQ changes. And here we introduce a bit more notation, sort of reflecting this idea that we saw this with positions, right? Positions were relative, right? IQ. Velocities are absolute, Q. We do the same here by just saying capital omega, the angular velocity of body B. And I don't have this here, but it's very easy to show that it would be the same matrix against any inertial frame of reference, right? This doesn't matter what I use here for I prime, I2, doesn't matter. I always get the same result. So I write this here as just capital omega B, the angular velocity of body B expressed in B coordinates multiplied with this vector. And then this would give me the velocities of arbitrary points on the body. So the idea here is similar to this idea of having the velocity of a point B, right? Where I don't have IB, but I just say V of B, velocity of B. And then I can do the same for the acceleration. Same idea, don't have to go through the details here. This will be actually for you good practice to apply the transport theorem to check whether there's a small mistake, maybe in these equations, who knows. And you would get this expression down here. So it gives me the position, velocity, and acceleration on any point on this body. And all I have to know to compute these quantities that we see in the summary down here is basically the position, velocity, and acceleration of point B. That's what we see here. The angular velocity and angular velocity and angular acceleration of my body, and this vector RBQ in B coordinates. And this guy here, that is fixed, right? So this I measure once, I compute once, and then it's always going to be the same. So it's a fixed value. And then these things here, those need to be given. There's the acceleration. So they are given to describe the motion of my body B. It's super useful because I basically need these 6 quantities, right, that we see over here. And these 6 quantities allow me to fully describe the motion of the rigid body. And what I mean with this is any point on the rigid body, I know what its position, velocity, and acceleration if I know sort of this vector RBQ, right? Of course, I need to know where the point is on the body, but once I know that, I can compute its position, velocity, and acceleration. We're almost done. But there's sort of an important thing that I glanced over. And it's happening between here and here. Where here, I wrote omega tilde dot, the acceleration of body B. Wait, no, not the acceleration of body B, the numerical derivative, right? I take the velocity, omega tilde B, expressed in B coordinates, and then out of this coordinates of the velocity, I take the derivative, right? Numerical derivative. That's what I have to do here. And then down here, I just drop the index, which somehow means I'm now talking about the physical derivative, the physical acceleration, right? And the entire time, I was trying to make a point that these two are not the same. So this is something that we need to look at very briefly. The difference between omega B tilde B numbers, and I take the derivatives, and what I would call the physical angular acceleration, right? I should not write this as matrices here. Let's write it as vectors. But I can always go from one representation in the other. But we should talk about vectors here, right? And so I have the physical derivative of this vector, which is a velocity vector. The physical derivative is an acceleration, and I express this acceleration in B coordinates. And if I think about the analogous in terms of translation, right, we would define the vector A, B, as the physical derivative of the velocity, right, which is expressed in B coordinates. So when I say A, B, and B coordinates, I mean the physical derivative of the velocity, i.e. the physical acceleration expressed in B coordinates. And my whole point, and we used it on the previous page, was that this is not the same as taking the numerical derivative of this vector. But if I apply my transport theorem to the rotation of the body, I will get here omega B dot, so the angular acceleration expressed in B coordinates, minus omega IB expressed in B coordinates, cross product with the original vector, which was omega B in B coordinates. right? Just blindly applying the transport theorem, and then we see something here.
Those two vectors are the same, and when we do the cross product, this is 0.
Yeah, right? I mean, they're the same, which means they're parallel. And this is 0. And we get that the numerical derivative of my angular velocity is equal to the coordinates of the physical derivative. And this is an exception that's important, that only holds for this vector. Right? In general, of course, we have to apply the transport theorem. Here, the transport theorem shows us that this doesn't make a difference. Why? Who can tell me physically, right? An intuitive reasoning why this vector is exempt from the transport theorem.
Is it because this angular moment is like fixed on a body B, and it doesn't, it's independent of I, and yeah, and that's why its numerical is equal to its physical?
No. No, it has to be this vector omega. This only holds for this vector omega, which is the angular velocity of my coordinate system B, right? Only that vector is not affected by the transport theorem, which is another word of saying that vector is not affected by the rotation of the coordinate system. And I think that makes physical sense, because if a coordinate system changes, rotates, every vector would have its numbers change, right? Every vector except one, which is the rotation axis, because the rotation axis is not affected by the rotation of the coordinate system, right? There's sort of this one exception that if I rotate a coordinate system, every vector seems to change, but the rotation axis doesn't, right? Because I rotate around that, so that rotation axis, that's why a door works, right? I have one axis that is stationary from the perspective of the wall and stationary from the perspective of the door. And that's basically what we see in this equation. And that's where I want to stop. Thank you for your patience. Have a good week. We see you on Thursday.